Our next speaker is Pranshu Gaba, and he will be talking about recognizing monoids of numbers.
Yes, hello. So I'll be speaking about recognizing numbers today, but the full title of my talk is recognizing monoids of numbers. So I'll go over these. I'll first define what monoids are, then what do you mean by recognizing monoids, and then we look at numbers. Okay, so let's look at monoids. So what are monoids? So monoids are structures that occur in abstract algebra. So monoid is a set M with an associative binary operation and an identity element. Okay, so it's like a group, but without the added condition that every element should have an identity. So I have a definition of a group here. So if you relax the final condition that every element should have an inverse, then you obtain a monoid. So every group is a monoid. So let's look at some examples of monoids. So I'll list some groups, they're all monoids. So if you look at Zn, that's a group. Yeah. The set of integers with addition is a monoid. The set of positive rationals with multiplication is a group, so also a monoid. So let's look at some monoids which are not groups. So the set of natural numbers, non-negative numbers with addition. So it must have the zero. Zero is the identity. Set of all rationals with multiplication is a monoid. And finally, this occurs commonly in automata theory. So let sigma be an alphabet, maybe 0, 1, or ABC. And so this is the set of all finite strings on this alphabet. If your operation is the concatenation operation and your identity is the empty string, then this is a monoid. Okay, so these are monoids. Let's look at what does it mean to recognize a monoid. So first we look at the string monoid. Okay, so we have the set of all strings. For simplicity, we'll just look at binary strings a comma b, and and we look at subsets of this. So a subset of strings is a language, and so recognizable subsets are nice subsets in a sense. So one definition that we have seen is recognition by a finite state automata. So if you have a finite state automata that accepts your language L, we call it regular languages. So this is one way to define recognizable subsets. So that is if you can construct a finite state automata that accepts your language L. And it has some nice properties such as they are closed under Boolean operations. So if L is regular, if L is recognizable, then its complement is also recognizable. And if L is regular, then it has a finite representation. So basically the automata gives you L. So this is well known. So we can look at this same notion from an algebraic perspective. So let's say you have a monoid M in general, and you want to see which subsets of the monoid are recognizable. So we looked at recognition by finite automata. Another notion is recognition by finite monoids. I'll define them shortly, but so the way you over here we recognize a subset S by a finite automata. Over here we recognize a subset S of a monoid by another monoid, finite. Yes?
Recognize means we will start running that automata and if you reach the final state?
Yes, so yeah, you start at the initial state, and we can, if you want, you can just look at deterministic automata. So each edge has a letter. You read the word one by one, letter by letter, and then you just look at which state you end up in. So this is I mark the final accepting state. Okay, so similar to recognition by automata, we can also have a notion of recognition by monoids. So we'll see how recognition by monoids works. Yeah, and this is an important result that these two notions coincide for monoids. Yeah. So let's say you have two monoids, M and N. I've added subscripts to distinguish the operations and the identity. And this is a morphism. So a morphism is a map between two monoids that maps the identity of the first monoid to the identity of the second monoid, and it basically distributes as well. So if phi of m1 dot m2 is equal to phi m1 dot phi m2 for all m1 m2. So these are morphisms. Now we can finally come to recognition by morphisms. So let's say you have a subset S, okay, of monoids, and you have a subset of, and you have a monoid N. What does it mean for S to be recognized by N? So S is recognized by N if there is a morphism from M to N and a subset T of N such that S is the inverse image of T. So if you look at this map, it takes elements in S to elements in T. It takes elements outside S to elements outside T. So if this is the case, then we say that S is recognized by this monoid N and this morphism phi. And in general, we are not given a morphism that recognizes your subset. So often we'd be interested in coming up with our own monoids that will recognize your subset. So in general, we'll say that you're just given M now, and you have a subset S. You'll say S is recognizable if there exists some N such that recognizes S.
Okay, but what if it's n equal to m?
M may be infinite. So
Finite.
we want recognition by finite numbers. So for example, strings, natural numbers, etc. And we'll just use this notation. Rect M is the set of all recognizable subsets of M. We'll let S in rect M.
See,
Huh?
if the monoid is given, the recognition will be clear.
In general,
That also.
yeah, it's,
And then on top of it, you want to actually find the.
we want. So finding the recognizable subsets is itself not easy. So that's basically the rest of my talk. I'll take some monoids and see. We'll try to find the recognizable subsets of those monoids. Yes.
So for the standard automata case, the graph of the automata itself is like the monoid or something. It's made up of states,
Yes.
and
So you can infer the monoid directly from the graph of the automata.
okay.
Okay. So first I'll state some properties of recm and then examples on the next slide. So yeah, just recm is the set of all recognizable subsets. So they are closed under Boolean operations. So if you have two sets S1 and S2 that are recognizable in M, then their union, their intersection, and the complement of a set is also recognizable.
This is because the images are the functions elements.
Yes, exactly. So again, so elements that are in the intersection, their pre-image is also in the intersection. So on. And there's another nice property that's yeah.
For this, you need both S1 and S2 to be recognized by the same monoid.
So you could, yeah, okay, yes.
Right? But you can
You
probably
can
build a product.
maybe combine that.
Yeah.
Yeah, and so if you have we have this nice distribution of the direct product. So the set of all sets that are recognizable, set of all recognizable subsets of M1 cross M2 are the direct product of the recognizable subsets of M1 and M2. And this is also, it's because pre-images behave nicely, this also. Okay, we can see examples now. So let's consider this language, which is the strings of odd length. Okay, the automata looks like this. It's a simple automaton. This is the accepting state. This is A1. And so what we'll do is we'll come up with a monoid that recognizes this same language, a finite monoid. And so this is like odd length, right? So it feels like we should have something like Z2 that recognizes this. So it is Z2. So I have written 0 and M. 0 is the identity here. M is the other element. So this is Z2. And so what do we need to do? So we need to define a morphism from our original language, which is right, which is AB star, onto this 0, M. So to define this morphism, it's sufficient to define it on the generators, which is just A and B. And because it's a free monoid, there's a unique extension to the entire monoid of strings. So here you see A and B are indistinguishable. It doesn't matter like whether you read A or B, only the lengths matter. So you can see that in the monoid as well. You map both you map both A and B to M. And here's an example how you would evaluate phi on a string. Because it's a morphism, you can open it up. You get MQ, which is M. So here we say that our language L1, which was a subset of AB star, is the inverse image of just M. So it's recognized. So we look at a more advanced language. So we are still looking at odd length strings, but it should begin with an A. And this is an automaton that accepts that. So if you see a B, then initially, then there's no way you can accept it. So you go to a dead state, a sync state. Otherwise, you are looking at odd length strings. So yeah, so this is, so can you guess how many states, how big the monoid recognizing this would be? How many elements? 4, okay. Any other guesses? So, okay, it's not 4, it's 5.
This one will be a monoid, the previous one was a group.
Previous one was a group, yes. This has to be. Okay, why is it 5? So it's not immediate. It's not like the number of states in your automaton should be equal to the size of a monoid. That's a good guess, but yeah. So what are we doing? So for each letter, so there are 2 letters A and B here. We look at their action on every state. So the empty string, if you read the empty string from each state, you stay in the same state. So that is one action, the empty action. So another action is reading A. So from Q1 on reading A, you go to Q3. And from here you go here, from here you go here. And from Q1 you go to here. From Q2 you stay in Q2. So we look at all different words. So what are the different actions that can happen? And for each action, we get a state in the monoid. And yeah, so once, I mean, you could verify this. I'll skip this, but so if you map A to P and B to Q in this monoid, and if you look at the inverse image of P, then indeed you get the desired language. Okay. So so far we have seen recognition of monoids of strings. So I'll finally come to my topic, which is okay. So yeah, this was the first one. So the empty string reserves every state. So there's an action of A, and then if you read the string AA from a state, from every state, you have some different actions. So turns out there are 5 different actions. So you have 5 different states. Okay, so I'll now come to monoids over numbers.
But,
Yeah.
can you show me how the morphism maps to A and B?
So I've defined phi for A and B.
Yeah.
So there's a unique way to define phi for words. So what's your question?
By P and Q, the generators of the monoid.
Yeah, I don't think they are generators of the monoid.
A and B are generated of this one.
Yeah.
Yeah, so if you read A, you reach P. If you read A again, you'll stay in P. Yeah, so now it alternates between R and P and R and P. So we want the inverse image of P. So it's like if you read a B initially, then you'll stay between states S and Q, and they won't appear in your language in the inverse image. Okay. All right. So we are done with strings. We'll look at numbers now. We look at many different monoids over numbers. So first we'll look at additive monoids. So there's integers, rationals, reals, complex, and I have the non-negative analogs on the right side. So non-negative integers, non-negative rationals, and non-negative reals. Yes.
Hi, so for the previous one, what is so general that for DFA is that anything you can written as a DFA is a monoid?
Yes. Yes. So those two notions coincide. So if you have a regular language, you have a DFA accepting that language, and you also have a finite monoid that recognizes the language. It's if and only.
And what is the monoid size? Is it like any bound on that? Is there any state in an automata?
The size of the least automata and the size of the least monoid are exactly the same.
That's fine.
I mean, it may not.
The size of the
But
least thing exactly the same.
The marginal kind of process.
But how do you get a smaller? This is a minimal automata.
Then R by A isn't that just a P square?
You need 5 different elements in the monoid. So there is a state where you are here and you have not seen any letter. That's the epsilon state. There's one where you have seen A. If like A corresponds to the when you have seen A and you have an odd length. A corresponds to the fact where you have seen an A initially and you have seen an even length string. B and BB correspond to the strings where you start with B and you have seen an odd length string and an even length string respectively. So there are 5 different kinds of states you could be in.
So why do we need odd and even for standard language?
So because in the end we want to accept only strings of odd length.
But if you start with a B, anyway you will reject.
So why are A and B?
So, but if you once you see an A, after that you have to keep track of how many B's you have seen.
No, if you started with a B, then you don't care, right?
Hmm.
So B and you also want to keep track of multiplication, right? I mean, like the thing that you might have started even, and then now it matters whether you see an even number of B's or an odd number of B's.
The total number of objects.
Yeah, so you need to keep track of the non B's.
Yeah, so A even has to be there.
So A is the action when you see 2 A's. And BB is when you see two Bs.
Yeah, so
So they have different outputs from the initial state. Right? Initially, if you see AA, you reach Q4, and if you see BB, you reach Q2.
yes, so isn't that
Started with A. Now you want to accept ABP. So if you just see B, you should reject it.
yes, so what I'm asking is, if AL leads to the monoids with R, and a single is leads to E, then isn't R just P square? So why do we give an R?
But that's a different element.
No, but that's a different element that
We get rid of S and
That's a different element in the monoid. P is not equal to R. P is R square.
you get rid of S and you make Q the same. You just on the remaining SS with Q.
Oh,
Okay,
No.
I think we should move on.
yeah. Okay. So we can discuss that later. So yes, the left side are the positive, negative, zero, everything, and right side is only the non-negative monoids. So we'll start with all integers. Okay, we want to characterize our goal here is to characterize the set of recognizable subsets of integers. This monoid. Does anyone have a guess? Okay. So what are the recognizable subsets of this monoid integers? So for example, if you have a monoid of strings, the set of recognizable subsets is the regular languages. So what subsets of integers would be recognizable by finite monoids? Yes.
plus some finite.
Yes. No. So that's for non-negative integers. Okay, I'll come to it. So
It should also be the same as I think the set of all unity regular line.
huh?
It should be 1% unity regular line.
That is for positive, non-negative integers.
Oh,
Yeah, I'll come to that. So here, so this it turns out is exactly the set of periodic sets. So we'll prove it. So let S be a recognizable subset. Okay, and suppose this is a definition. So there is a finite monoid n, and there is a subset T of n such that there is a morphism from Z to n such that S is the inverse image of T. And now I'll make some claims. I'm claiming that n must be a group. Why is that? Because Z is a group. So if you look at phi of n and phi of minus n, these two elements should like phi of n minus n is phi of 0. So these morphisms in general take groups to groups. So n must be a group, and moreover, phi is completely determined if I just give the value of phi 1. Why is that?
No, so this marking is an on-to, that is why.
It doesn't have to be on
Because
this.
n is the large value, much larger than we should not get, why would we?
because he's just telling you what the inverse image
No,
of
but
it is.
there might be points in n which are not mapped.
Can a group be a subset of a non-group monoid?
Okay.
It has to be on to one.
Yeah,
If it's
so the, yeah,
Okay, if it's on. Can a group be a subset of a non-group monoid?
A group could be a subset of non-group.
Okay, suppose if we can assume it's on to. Yeah, and phi is completely determined by phi of 1. So indeed, because if you take any integer n, phi of n is just phi of 1 multiplied by itself, monoid multiplication. And now I claim that this implies that S is a periodic set. By periodic, I mean there exists some P such that for all n is in S if and only if n plus P is in S. So where is this over? So the period here, in fact, is the order of phi of 1 in N. So if phi of 1 let the order of phi of 1 be something, let it be P, then phi of 1 plus P will have the same mapping as phi of 1. So you cannot separate any two integers that are separated by the order of phi of 1. So this is always a periodic set. Yeah, this is like an analysis for recognizable subsets of integers.
So definition also allows the union of periodic sets are also union.
So that is included in this definition, yes. So for example, a set of all integers, there are 2 or 3 mod 5, that is a periodic set. So 2, 3, 7, 8, 12, 13, that is a periodic. Yes?
So when you say you're considering for what you do.
No, Z.
If you say for all in Z, so you have to find 2, 5, 1, 3, and for 1 and 1. But basically you're saying 5 minus 10.
Oh yeah.
5 1 to the 5 minus 1.
Phi of minus 1 to that. You're right. Yes. Yeah, you're right. So this is periodic set. How much time? Okay. So I'll look at n. So let's look at non-negative integers. So this is a cool observation that this non-negative integers with addition is actually isomorphic to the string monoid where we are alphabet size 1. So this is the same as unary regular languages, and these turn out to be ultimately periodic. So you can have a finite number of elements, but in the end, eventually, all elements that are in your set, they are periodic. Yeah, this is interesting. So I'll move to Q. Let's look at rationals, non-negative rationals with addition. So this is a group, and like before, if a subset is recognized, it must be recognized by a group. Okay. If it's an onto recognize it. And okay, so this is an important observation. So this is an arbitrarily divisible group. So what do I mean by that? So if you take any element, any rational number Q, you can split it into itself k times for any k. Now, so I'm claiming that this implies that if you have any recognizing morphism from Q to G, then it will map every element of Q to the identity. And this is because you start with any Q, you write it as R times K, where K is the order of R in the group. And now this is the identity. So it implies that, yeah, it shows that Q is mapped, every rational Q is mapped to the identity. And this gives us that the only recognizable groups are the trivial, the only recognizable subsets are the trivial ones, the empty set and the.
You are saying that there's no finite subgroups.
There is no finite. Yeah, you won't have a finite. With this operation, you won't have. With addition.
Follow that. So what are we doing? So you pick an arbitrary Q.
Arbitrary Q, you can divide it into k parts. So it's R times k.
For what K would be?
So this is a finite group. G is a finite group. So let R be a R. Look at the order of phi of R in G.
You can exactly tell that, right? Or you choose a K such that whatever every element of G power K is identity.
Yes. Okay. Yes.
And
That exists.
and then you take the R of one. Okay.
So every rational is mapped to identity. So these are the only recognizable subsets are the trivial ones. And same argument holds for reals and complex also. So there as well, the only recognizable subsets are.
One doubt.
Yeah.
Is the previous one to one? Is the mapping 1 to 1?
Which mapping?
For the so changing a K, where we need K for every Q or.
No. So K, you can take K to be the order of the group. Yeah. Okay. So these are the trivial subsets. I'll skip over this because I want to show. So we looked at non-negative rationals also, and turns out the recognizable subsets are there are only 4 of them: empty, everything, 0, and positive rationals. Yes, I'll quickly go over multiplicative monoids. So we also looked at multiplicative monoids, so integers, rationals, reals, and complex numbers. So the way to analyze this is to go from these monoids to these groups. Are these groups? Yeah. Yeah, they are groups. And you can also go to just positive versions of those groups.
The first one is not a group.
First one is not a group. Yeah, no, these are groups. This is not a group. Okay, so this real numbers is easier to analyze. So I'm just showing how you go from reals to non-zero reals. So if you want to look at the recognizable subsets of reals, those are the recognizable subsets of non-zero reals, along with each recognizable subset of non-zero reals with 0 added. And yeah, so if you look at non-zero reals, you can write non-zero reals as positive reals with a z product with z2, and this is now an arbitrarily divisible group, and this is a finite group, and we get okay. Just this last slide. So how do we find the recognizable subsets of integers or rationals in multiplication? So the same technique as reals does not work, because in multiplication rationals are not divisible. So you cannot divide half, cannot write half as a product of 2 rationals, non-identity rationals. So this, we haven't really found the answer to this, but this is the idea that we had. So you can simplify this n to non-negative to positive natural numbers, and then
Two times one by
okay, no, we would like to write it as a product of the same number. So 1 by root 2 times 1 by root 2. Yeah. And so yeah, so our observation is that if you take any positive number, you can write it as a finite sequence of non-negative numbers, but now with the operation addition instead of multiplication. And this is just prime factorization. And then it's easier to work with addition than multiplication. And same thing works with rationals, but now you can write each positive rational number as a finite sequence of integers, where the where the ith value gives the power of the ith value. So yeah, that's it. So we looked at recognizable subsets of sets of numbers. Thank you.
So did you arrive to any character
Or
general or some?
not general. So we looked at each case separately.